Hi, I'm Ruben Iglesias, and in this part of our AOS-CX 10.8 update, I will be introducing Precision Time Protocol. Our agenda is an overview, details, deployment models and recommendations, configuration, demo, and finally a troubleshooting section.
So first of all, what is Ptp and why is it required? There are applications and systems that used to be completely analog and that have been moving from the analog world into the networked IP-based world. And in some cases, not even IP, directly Ethernet world. Some of those applications and some of those systems require a level of time synchronization between the devices involved in those systems that a time synchronization process like NTP cannot satisfy. So those requirements are much more strict. And for example, if you look at NTP, you will be moving into an offset of the tens of milliseconds. And some of these systems need to go down to a precision of tens of nanoseconds in the synchronization level. So that is called the offset. And let's define the offset right now, because this is the most important concept in Ptp. The offset is the time difference between the clock that you're looking at and its reference clock, its parent clock. So the full purpose of Ptp is to reduce that offset as much as possible, and to do that in cycles that are very close together. So for example, the default in the most common deployment is 1 second. So every second you will be each one of the clocks on the devices in that system will be discovering their own offset by means of Ptp. So they will realize how much they have deviated from the reference clock, and then they would adjust the clock. So the process would be discover the offset, adjust the clock, discover the offset, adjust the clock, etc. So that is the key to Ptp. So some of the elements that you will see here is that there is a group of products in the market that is called the grand source clocks. Actually, they're called the grand master clock, but in Aruba, we are moving towards inclusive language, and we have replaced the words masters and slaves that are usually used in Ptp, and we're using the words source and sink. And the word sink is as in the kitchen sink. So it's S-I-N-K. So that's the sink. That's the receiver of a time synchronization process. So Ptp starts at the top with some of these grand source clocks. And a grand source clock is a high precision clock that is also synchronized to a universal source like a GPS network, and will act as the reference clock for the whole system. Ptp is the protocol that will be used between the grand source clock and all those devices in the system that we're trying to deploy or that we're trying to maintain. All that synchronization process between that grand source and these other clocks that are called ordinary clocks happens by means of Ptp. So Ptp is the transportation protocol for that synchronization. Let's take a look at some of the details of all of this. First, let's look at the clock roles and types. The roles, there are basically sources and sinks, as we mentioned before. A source provides clock synchronization information to other devices on the network, and a sink is the receiver of that clock synchronization information from a source. The ground source clock, as we mentioned before, is a high-precision clock that acts as the main clock synchronization source for the network. They're usually deployed in pairs, so there is redundancy in the clock source, so in the overall reference for the network. In terms of clock types, we will take a look at 3 types. The first one is called boundary clock. A boundary clock is a network device that is both a source and a sink. It is a sink in relationship to an upstream source, and it synchronizes its own clock using Ptp, and then it uses its own clock to become a source for other devices downstream. And here I use the terms upstream and downstream in terms of the flow between the ground sources and the ordinary clocks or the clients. Transparent clock also sits between the ground source and the ordinary clocks. However, it is neither a source nor a sink. A transparent clock sits in between a source and a sink. It receives Ptp synchronization messages from an upstream Ptp device. It transmits those Ptp synchronization messages to a downstream Ptp device, but it does not synchronize its own clock using Ptp, not necessarily. The only thing that is important here is that those synchronization packets are modified by the transparent clock by adding a timestamp, an additional timestamp that represents the time that that packet took to transit that transparent clock. So between the reception and the transmission of that packet, that time is called the resident time, and it becomes a timestamp that will be added to the packet before transmission. An ordinary clock is what we call the Ptp client, and it's also, so that is the actual purpose of the whole Ptp system. These are the devices that actually need to be synchronized to that source, and most importantly, usually among each other. So you have a set of ordinary clocks. These are all your, this is all your system, and that requires that synchronization. So whenever you have a sink, a device that needs to be synchronized against a reference clock, if you have redundancy in those sources, the sink will need to select one of them as its source, and in the case of having 2 exactly, the other one will become a standby. The process to select the parent clock starts by looking at a user-defined value called priority 1. It is just a number that you can add to your reference clock, and smaller values here indicate a higher priority. Then after that, if the priorities are tied, then it will go through 3 values that are part of the clock quality, and these are class, accuracy, and variance. And these are embedded in the clock by the manufacturer, and they are values that you cannot change. Then priority 2 is another user-defined value. It will be the tiebreaker if everything above it is the same. And finally, as with most things in networking, the final tiebreaker is the MAC address. So the unique identifier of the parent clock is the MAC address, and a smaller MAC address will be used to select the source. Ptp, of course, uses messages to exchange synchronization information and also to maintain the whole Ptp system working. Here you see that there are some message types that are event and general. The key difference here is that event messages are those that contain a critical timestamp. So those are the critical messages that need to be processed for Ptp to work. The rest are there and will form part of the Ptp exchange. However, they have not a timestamp, so they're not critical in terms of delays, etc., across the network. By the way, these messages can be transported over Ethernet, or over IPv4, either multicast or unicast. In all the cases that we are offering today in 10.8, the most common deployment is over IPv4 multicast. Anyway, if it's over IPv4, unicast or multicast, all of these messages are transported in UDP packets using either port 319 for event messages or 320 for general messages. Now that we have an idea of these messages, let's take a look at the synchronization process itself. Let's first look at any time source and any time sink that are directly connected. And here you see that there are two parts between T1 and T2. There's a first either one single message or two messages, and that depends on how the system is configured. If it's configured as a one-step synchronization process, the T1 timestamp, so the time in which the sync message was sent or transmitted, is stamped into the sync message itself. However, if you're using a two-step method, then a follow-up message will contain and bring the T1 timestamp. So the time sync, at this point, it will receive the sync and it will have both values, T1 and T2. And it will be able to calculate both the time that the packet left the source, but also the delay of that transit between the source and the sink. Now, to get more precision on the delay, the sink sends out to the source a delay request message, which is also an event message, and it's timestamped with T3. And then the time source will respond with a delayed response. And all of these data, T1, T2, T3, T4, the first delay and the second delay, are all used to calculate the offset. So you see that there's the sync will do all the computation for the mean path delay, and the offset will use the time 1 and time 2 and the mean path delay to calculate the offset. So the offset will be the difference between the source and the sync clocks, and the best and how Ptp calculates that is by means of this number. So this is the amount of correction that the clock will apply to itself, that will adjust itself to be in sync with the source. And this process will be repeated again and again and again with Ptp. And this is what will happen between two adjacent clocks, so the source and the sync. However, if you have a transparent clock in between, the process is a bit more complicated. Remember, the source and the sync are now different, several hops away, 2 or more, and in between you have these transparent clocks here. In this case, I have 2, but you could have more. So the difference is that T1 is transmitted from the source in the sync message or the follow-up message as before. But now, as it goes across the transparent clocks, either the sync or the follow-up will contain also the path delay 1, so the path delay between the time source and the first transparent clock, and the resident time of that packet inside the transparent clock 1. And the same will be repeated. So all of that information, the path delays 1, 2, etc., and the RTs are going to be coming in the either the sync or the follow-up and will be received at the sync. So the sync will have all of this information plus its own reception time. And now the delay request will have a similar process going end to end and then back. So with that, we have an understanding of the synchronization process between two adjacent clocks and between two clocks that are mediated by one or more steps of transparent clocks in between. And this is just a summary of that. So what do we support in 10.8 in terms of Ptp? First, what clock types do we support on each switch? The 8360 switch series support boundary clock and transparent clocks. There is an exception. The copper port models of the 8360 do not support Ptp. The 6300 switch series support transparent clock mode, but not boundary clock. In terms of compatibility and interoperability, Ptp and VSX are mutually exclusive today. However, Ptp and VSF work well together. So they are compatible and interoperable. On the right side of the slide, we have the profiles that we support. And you'll see this in the next slide. But a profile is a set of parameters and value ranges that are applied to a Ptp configuration. In 10.8, we support 4 of them. We support the 1588 version 2, which is the standard or the default profile that most vendors use and support. But then we support 3 more. We support the ST2059-2, which is a profile created by the Society for Motion Pictures and Television, and its application and need is self-explanatory, right? It's required for professional broadcasting environments. It provides the parameters for Ptp for those particular applications. The AES-67 profile is the equivalent for audio engineering, and it was created and defined by the Audio Engineering Society. And finally, the AES-R16 profile is a set of parameters that will allow for Ptp to be used and synchronize clocks that support both the AES-67 and the ST2059-2 profiles. Here's an example, and this is just for reference here, and you can look at the slide deck if you want and find these values. These are the values that are supported in the profiles, the minimum, maximum, and default values for these profiles. Normally, when you configure a Ptp on a switch, these values are not changed, and unless the client devices, the ordinary clocks, require a change. In that case, you will propagate the values from the ordinary clocks up the chain to the grand source. Ptp messages, as we said before, can be transported over Ipv4 Multicast. And in that case, the multicast address will use for all messages except peer delay messages, the address 224.0.1.129. And for peer delay messages, it uses the 224.0.1.107. And you will need multicast routing if the source and the sink are on different IP subnets. If they are adjacent and they talk directly to each other without any other devices in between, multicast routing is not required in that part of the network. For PTP, it might be required for other applications, but for example, if you have a boundary clock directly connected to a ground source clock, multicast routing is not required. If you have a boundary clock, a layer 3 transparent clock that is routing, and then you have your ordinary clocks connected at the end of that chain, then multicast routing will be required. And we will talk a little bit about the recommendations for that configuration later. Ptp can also be transported over Ipv4 unicast, and in that case, you have to configure the peer IP addresses. Today, Ptp over IPv6 is not supported, and Ptp over Ethernet is supported today. However, none of the profiles that we support require Ethernet. They can all run over Ipv4 multicast. So it will depend on your ordinary clocks if you select Ptp over Ipv4 multicast, unicast, or Ethernet. So some deployment models and recommendations. Let's start with some general guidelines. The deployment models and guidelines that we present here are the result of our network testing labs trials and are the recommended designs and configurations. Of course, if you have an existing network, some of these might vary, and you may need to make some adjustments. Please consult with your Aruba representative and system engineer to make sure that you're having a network that will satisfy your Ptp requirements. Let's get into the some general guidelines here. For IP multicast-based Ptp time distribution, use PIM sparse mode. If you are connecting a transparent clock and a boundary clock, ensure that the transparent clock becomes the DR by setting the DR priority for PIM. Ensure that the M routes are programmed on TCs so that there is reachability for Ptp streams from the upstream. And finally, configure static IGMP groups on TCs if the clients themselves will not be sending IGMP joins for the Ptp multicast group. In terms of QoS, the 8360s, when they behave as boundary clocks, and many ground source clocks in the market will pre-mark the Ptp event messages with a DSCP value of 48 or a class selector 6, which is the same. So if you're configuring the receiver of those packets, configure QoS Trust DSCP to provide the right priority level, especially if you are talking about transparent clocks, or if for some reason you have in between two Ptp clocks, you have non-Ptp switches in the path. So now we will see 3 deployment models, and pay attention to the notes on the multicast configuration. So the first one is a simple deployment in which you have a 2-layer network for Ptp in particular that will connect directly at the top. So your core devices are going to be boundary clocks, in this case 8360 switches, and will be connected to 1 or 2 ground source clocks. In this case, we're showing that the ground source clock 1 is active and the ground source clock 2 is standby. And those dotted green arrows are the paths that we expect Ptp traffic to use by default. So we have the boundary clocks at the core, talking directly to the ground sources. And then between the cores and the ordinary clocks at the edge, we have layer 2 switches working as transparent clocks. These could be 6300 switches in general for campus applications. and they can be VRF stacks. If this is a data center application, these could be also 8360 switches acting as transparent clouds. In this case, because we do not support VSX, pay special attention to PTP, to spanning tree with PTP, because we need this to be loop free. So spanning tree will be required for this topology. The other thing is that on the boundary clocks, you will have to configure a Ptp Vlan that will be the VLAN that will be transporting the PTP messages, because the downlink from the core is our layer 2 links. So that is not required at the top because the connection between the ground sources and the core are layer 3. However, here at the bottom, we will need a spanning tree between the boundary clocks and the transparent clocks. And also use VRRP together with spanning tree to provide that layer 3 redundancy also there. And multicast routing for PTP in particular is not necessary in this deployment. It might be necessary for other applications where there are other paths, routed paths involved. Remember, here we said that there is no need for multicast routing. However, we recommend that you enable IP-IGMP snooping and that you add a static group to snooping for the event messages or for all the PTP messages, 224.0.1.129. A similar deployment, but with layer 3 access switches working as transparent clocks. So the whole topology is the same, except for the access layer being a routed deployment. In this case, many things are similar. However, we need multicast routing between the boundary clocks and the ordinary clocks. For that purpose, the boundary clocks or the core switches will become PMSM routers. So we want them also to be the BSR and RP candidates using the loopback interface for reference or for source. All PTP interfaces will need to be PMSM enabled. And one thing that we didn't say in the previous slide, but also applies there, is that if the downlinks are lags, link aggregation groups, or whenever you have link aggregation groups that work with PTP or that transport PTP, one of the ports will have to be a primary, and the other one will be a secondary. So you will take two ports and define them as PTP primary and secondary respectively. And if you have more ports on that same link aggregation group, they will not participate in the PTP conversation. So the primary will be the one transporting PTP. The secondary will be the standby. And in this case, there's no need for a Ptp Vlan because this is all layer 3. Notice in the layer 3 access that all Ptp interfaces will have to be IGMP querier, and we'll have the IP-IGMP static group for the same multicast address. And of course, the transparent clocks need to be PMSM routers. And as we said before, in the general guidelines, on the SVIs or any interface that supports PTP on the transparent clock, add the DR priority for PIM sparse. This is a different approach with 3 tiers, all layer 3. However, notice that at the top, we have transparent clocks. So the actual spine and leaf network here is our boundary clocks. So both leaves and spines are boundary clocks. However, we use between the ground source clocks and the spines that act as the first layer of boundary clocks. We use a couple of switches that could be 8360 in this case, but could also be 6300s depending on the performance needs you have. And they will be there participating as transparent clocks. And the main idea here is that they will be providing the redundant paths for PTP for the whole network. And spines and leaves, as we said, are boundary clocks. And this is the first model we are presenting in which you have more than one layer of boundary clocks. Notice that in all three deployment models that I'm showing here, all the devices in the network between the ground source clocks and the ordinary clocks are PTP enabled. And then in terms of multicast routing, because everything is layer 3, we follow the same rules that we showed before. The transparent clock will be a query, will be PMSM enabled on all PTP interfaces, and will also be the PMSM router in this case. And then you see here that we are recommending that you change the priority 1 on the first layer of boundary clocks and to a value of 10, and the same thing on the next layer of boundary clocks. So with that, we have the recommended deployment models. Let's take a look at some configuration details. And this is not going to be exhaustive because we're going to go and show you one demo after this. So let's start with a boundary clock. This is a basic configuration. And in this case, we're using a boundary clock. We're deploying a boundary clock using an 8360 switch. And we're using a two-step process. We're using multicast IPv4. And the only thing that we need here, so the profile that we're using is 1588 version 2. And then in this slide, we're also showing, besides the profile configuration, notice that we are not changing any one of the default values of the profile defined in the profile that we have shown before in that table with all those values and ranges. So we have interface 1 and 2. These are the two uplinks. In this case, they are connecting the boundary clock to the ground sources, to the two ground sources. And the only thing that we do here is enable PTP. The next step in the boundary clock is the downlink. In this case, we're looking at a link aggregation group connecting to a 6300 switch that will be working as transparent clock. And we're using a layer 2 connection. So that device is working in layer 2. So we will define this as the lag as no routing. And in that case, we are defining the Ptp Vlan 240 to transport PTP. Then again, this is a link aggregation group, we are defining one of the ports as primary and the other member as a secondary. Notice also, I haven't seen, or we talked about this before, but if you look here, the source interface that we're using for PTP is always the loopback 0. Could be another loopback interfaces, but it's recommended that you use a loopback interface. So let's take a look at the 6300 device working as a transparent clock in layer 2 mode. The profile is similar to the previous one. Just notice that it's using 1 step instead of 2 steps here. And the mode is transparent. We're also using the same profile, of course. And then we have the link aggregation group. This is the uplink. And the uplink, or the connection to the boundary clock, does not require the Ptp Vlan. And the only thing that you need to do is to enable Ptp. And if you look at the port members, there's no need to define the Ptp lag role. All of this is because this is a transparent clock, and it will be receiving everything through the VLAN 240 and also through one of these ports, depending on how you configure the previous hub. And these are the ports that connect to the ordinary clocks. And the only thing that you will have here, again, this is a layer 2 transparent clock, is enable Ptp, and you're good to go. So optimizing Ptp. As we said before, we recommend that you use QoS Trust DSCP, especially on transparent clocks and non-Ptp switches. In most cases, you will see that you are receiving the packets, the DSCP event messages with a DSCP of 48, and the 8360 switches, when they work in boundary clock, they do that marking, and this is how you see the package. So this is a typical Ptp sync message received from an 8360 switch that is working in boundary clock mode, and you see here the class selector 6. And by the way, this is, as we said before, a sync message, but any event message will have the same class selector. General messages will have a DSCP of CS0, so no prioritization at all. Protect Ptp, especially in boundary clocks, we recommend that you use the defaults. So the 8360 has a default configuration for the control plane policy, and for the Ptp class that is predefined, the defaults are a priority of 5, a rate of 1,000 packets per second, and a burst size of 250 packets. However, here's the key. Whenever you add more boundary clocks, whenever you add more syncs to this device, so every time you add more clients, Ptp clients to this boundary clock, check if you're starting to drop packets. So run this command, show COPP, statistics, class Ptp, and take a look at the package drops. And do that for several days after deploying new clients. And remember, clients could be ordinary clocks or other boundary clocks. And the number of packet drops here is key. If you get more than 0, just one drop packet, take a look at the rate and think of changing it, increasing that packet rate, so you do not drop any Ptp packets. Drop packets in Ptp on a boundary clock means that your synchronization process will not have the accuracy and the precision that is required by your clients. So let's get into the demo. So the demo, in this case.
Before jumping into the demo, let's take a look at our layout. The network that we will test is a network with one boundary clock and one transparent clock. The boundary clock is here represented at the top right, and it's an 8360 switch. And then the transparent clock is a pair of 6300 switches in a VSF stack. We are, in this case, using a layer 2 connection there, so the transparent clock is working as a layer 2 switch. And the reason for that is that I want to show the the need for using that VLAN 240 and how we use that in Ptp. If instead of this you had the transparent lock, in other words, the 6300 VSF stack working in layer 3, then you would have to follow the configuration steps that we showed for multicast when the source and the sinks are not on the same subnet. In this case, that part is not necessary, but we are exchanging that for some of the things that you need to do when the transparent clock is in layer 2 mode. Now, notice that in this case, the source, that is the boundary clock, and the sinks, that is the ordinary clocks on the Ixia box on the bottom left, are on the same subnet. And then we have two more subnets. The grand source clock acts as a source for the first sink in the 8360, and this is going to become our active grand source clock, the top left in the Ixia box, and then we will have a backup or standby grand source clock for our boundary clock, that is the other port on that Ixia, and that will act as a backup or standby. So with that, let's get into the demo. Let's take a look at how all of this works and what you can see in our switches in terms of Ptp. Let's start by taking a look at the Ptp configuration on the boundary clock. So we're looking at the console of the 8360, and we're running the show run Ptp command. First, you'll see that we have the profile. In this case, we're using the default profile 1588 version 2. The only things that we are doing here, the basic and necessary steps, are to enable the profile, then to select the clock. You can select 2 steps or 1 step. Remember, 2 steps means that right after the sync message, the source clock will send a follow-up message to improve the precision of the calculation of the whole process. So then we have transport protocol. In this case, we're selecting IPv4. If we don't do anything else, this means that IPv4 is multicast. So we will be transporting the Ptp messages using multicast. Finally, we configure our switch in boundary clock mode and with end-to-end delay calculation or delay messaging. When we go to the uplinks to the source, we have Ptp enabled. This is the only parameter that we will be using. There are other parameters that you can configure that we've already seen, but for the basic configuration, this is more than enough. So because all the other parameters are set by default when we select that the profile that we're using is 1588 version 2. This is one of the advantages of using profiles, that the default parameters are usually very good for the application that you are running. Next, so that is true for both of these ports. And then we have a downlink to the next hop in the Ptp network, which in this case is our 6300 that is working in transparent mode. And you see that what we're using this is a link aggregation group that is working in layer 2 mode. Because it is working in layer 2 mode, besides just enabling Ptp, we need to add a VLAN for Ptp transport, for Ptp messaging. So this is necessary, and if you do not define a VLAN, Ptp will not work. Then on the members of that link aggregation group, you will select 2 of the members, and one of them is going to be the primary, and it's going to be the active messaging port for Ptp, while the secondary will stay in standby mode and will only take and start transmitting and receiving messages if the primary goes down. So remember, in this case, we have a link aggregation group that is working in layer 2, and this is our downlink to our ordinary clocks across the 6300 with a transparent clock. And we are configuring the Ptp Vlan because it's layer 2, and then the member ports are, one of them is going to be our primary and the other one is going to be the backup, which we define as secondary. We also define here a Ptp interface for the source, and in this case, we're using the loopback interface for all of that. So we can use the loopback IP address as the reference for the message. One more thing that you might want to check here that is recommended is to show the QoS configuration. So let's say show class commands. And in this case, I created a class IP Ptp. Ptp is just the name of that class. And what I'm doing is I'm using this class to select UDP packets that are using the port 319. Port 319 for UDP is the event messages, the Ptp event messages. And remember, event messages are the ones that are transporting critical timestamps. So that would be basically the delay request and the sync message. Where do we apply these? We will apply this. Let's take a look. So we do show policy, Ptp poll, which is the name of the policy that I'm using. So let's take a look now at the policy. The policy, we take a look here, and we see that I'm applying local priority 5. So we're elevating the priority of the Ptp packets that we defined in our class up here. Then with the show policy Ptp poll commands, remember Ptp poll is just the name of that policy. What we're doing is, again, applying local priority 5 to these packets. And then we are applying this policy on the uplinks, so the links that communicate with the grant source clocks. So that's ports 1 and 2. And then on the downlink for the lag 240, which is the one that takes us to the transparent clock, and across the transparent clock to our ordinary clocks or clients. So with that, we have the whole configuration. There's one more thing that you might want to watch in the boundary clock, which is, and it's extremely important in the boundary clock itself, because you can have many ordinary clocks synchronizing and using the boundary clock as their time source. So COPP, because remember that all the packets are processed by the CPU. So COPP, and we'll take a look at the factory default. And we'll just go down until we find Ptp. And here we see that Ptp is configured with a priority of 5, a packet rate of 1,000 packets per second, a burst of 250 packets, and a hardware rate is the same as the rate that we have in software. So that configuration should be enough for a medium and small size network. And I mean that from the Ptp point of view, the number of clocks that use this particular boundary clock as their source. But if you want to monitor if this is working fine, then we will take a look at the statistics, and we will be looking for dropped packets. You see here, I have my default policy. This is the same that we saw above. But when I look at the actual dynamics, we had over 1 million packets and we dropped none of them. So this means that the configuration we have for COPP, for control plane policies, is good enough and it's working fine. But if you see that you start dropping packets here, then you have to make sure that you improve at least the packet rate and probably double it to 2,000 packets per second. Now we can take a look at the status of the whole clock. So let me first take a look at the status of the relationship between the boundary clock and the ground source clocks. So first, to check that, I will check the status of the Ptp ports or the Ptp interfaces. So show Ptp interface brief. And I see that port 1 is a sync. So it is actually or currently receiving information from the source. So in this case, the ground source clock, which is our Ixia box. The second port is in idle mode right now, even when it says that it's a clock source. So whenever a port is not behaving as a sync and acting as a sync, it will be shown as source. But source might mean it is an active source transmitting packets and sending clock information, or it's actually in idle mode and it's the backup for the clock sync. So you see the state of the 3 ports, and it's important that you see one of them as sync, because that means that it is receiving clocking information and timing information from a source. So it is an active participant in the Ptp network. So now let's take a look at the event log to see the level of synchronization that the switch has achieved with the ground source clock or the Ixia box in this case. So show event, will you display them in reverse, a sequence -D, and that allows us to select the Ptp daemon for the show event. So you see here that from the bottom up, we went through some steps. We started with the Ptp clock in holdover state. That was because at that point I had not started the source. So the source was not transmitting sync messages. So then the source came up, and actually 2 sources came up. One came up on port 1 and the other one came up on port 2. So port 1 became the clock sync. There was the selection there, and this is what we see in this command that I have highlighted here. The ground source or parent has been selected. And actually, because we are using the defaults and we didn't configure any priorities in the sources, we use the MAC address to select. So the parent that was selected is the one with the lowest MAC address. Now, and that is the one that is connected to port 1. Now, take a look at port 2. Port went to passive state, and then it moved into clock source state, which is the same we said before, that it is in idle state, waiting to become the sync if the current sync fails. Now, once that is done, the clock goes into acquiring state. Acquiring state means that it is starting its synchronization, its initialization process with the ground source clock in this case, or any source that it is above it. Then from the acquiring, it goes into an intermediate state that is called frequency locked state. And this is when they start
the phase, so they start the synchronization process. And once the synchronization process is finished, and there's only the maintenance sync packets going between the ground source and the boundary clock here. The clock is in phase aligned state. So phase aligned means we have arrived at a state in which we are synchronized, and now the only thing that we will be doing is doing these micro and nanosecond adjustments in every sync period, or in every sync sequence. So in this case, because we're running the defaults of the 1588 version 2 profile, this means that every second we will be having these alignments. So let's take a look at the state of the clock itself. Remember, this is a boundary clock, so it has its own clock, is synchronized to the source, and then it is going to be used to synchronize the sinks that are connected to it. So that internal clock will be used as the source for the rest of the network. So let's take a look at that show PTP clock. And show PTP clock tells us that the profile we're using, the boundary, so the PTP mode, boundary clock, the delay mechanism end-to-end, its own identity. So the sinks will see this as their source, and they will show you this particular MAC address there as their source or their parent clock. We're using IPv4 as the transport protocol. We're using 2 steps, and we keep the defaults for the priorities, which are for 1588 profiles. It's 128, both for priority 1 and priority 2. But the key here, what we're looking for is for this offset. Remember, the offset is the deviation between the internal source, or that the internal source measures against the source clock with the sync message. So once the offset is the end result of the synchronization process. And this again happens and is calculated every second. And as you can see, it changes from one cycle to the next. And the other thing that you might want to notice here is that it can change from positive to negative, but it's always in this case within the 100 nanosecond range. So that is a very precise clock, and it is following the source clock very closely. The mean delay, remember that the mean delay is another measurement that has to do with how long it takes for the sync message to go from the source to the sync, in this case, this particular clock. So again, this is very short, and again, this varies from packet to packet, because the network has different behavior in terms of nanoseconds and delays from one packet to the next. So and the steps removed means that there's only one hop away, so there's nothing in between the boundary clock and the source clock. So with that, we have everything that we need to see for the boundary clock. Let's take a look now at what's happening on the Ixia box from the point of view of the grant source. So we will focus on the top part here of our screen. We're looking at these 2 ports, 10 gig LAN 001 and 10 gig LAN 002. These are my 2 sources. And you see, if you go to the configuration here,
the clock roll, both of them are masters. Remember that we see that as source in our documentation, CLI, etc. Because the words master and slave are no longer acceptable for us. And so we have these two ports that are masters, and this is how we have the redundancy of sources for our switch. So in our switch, the 8360, our boundary clock, port 1 is connected to port 1, and port 2 is connected to port 2 of the Ixia. So we saw in the selection process that we had selected port 1, and that, if you take a look at that, you see that that port is up and the other one is down. And if you see at the state, one of them says that it's the grant source and the other one is passive. So let's take a look at, remember that we saw that there was a MAC address showing which one was the parent. So what we will do here is we will go to the Ethernet part of this and take a look at the MAC address. If you remember, the MAC address that we saw as the grant source that had been selected was started with 001101. And this is the one that we know now that is the source, the Ptp source for our boundary clock. So if I go back to Ptp, that port is the one that is up. And if I go to my switch, I can see that the source, so show Ptp parent clock, it is telling me that that's the MAC address of my grant source clock. So both the parent and the grant source are the same in this case because we have only one hop of clocks above us. So that's all from the point of view of the relationship between the grant source and the boundary clock. Now let's take a look at what's happening at the other end of this equation. At the other end, what we have is we have two ports in the Ixia box, and each port has 5 clients, or in other words, we have 10 ordinary clocks that are represented here by the word slave, and we call them sinks. So let's, and these are, you see here, the master clock ID. So it is showing this is the MAC address and the clock ID of the boundary clock. Remember that these ordinary clocks are connected to, from the Ptp point of view, they are talking to the boundary clock because the 6300 that is sitting in between does not participate in that conversation except for adding the resident time to the sync messaging. So with that, let's take a look at what's happening on the transparent clock here. So the transparent clock, we'll see here show Ptp, show run Ptp, and let's take a look at the configuration of this particular device. You see that the configuration here is a lot simpler. For example, the profile looks the same, but the only things that you have to do is clock step, transport, and the mode. The only mode that we support on the 6300 is transparent, always end-to-end. We do not support peer-to-peer mode, so the delay mechanism is always end-to-end. Transport protocol IPv4, and notice that the clock step is 1 step. So you might think that this could be a problem because if you remember, the boundary clock was configured as a 2-step device. However, the 8360 supports something that is called mixed mode. So it will use 2 steps to work with its own source, but it will respond to the 1-step configuration coming from the transparent clock and the ordinary clocks. Let's go and take a look at the ordinary clocks here. And you will notice that they are all configured in one-step mode. So the step mode is one step. And also notice that the sources were 2 steps. Then additionally, because we haven't shown that before, notice that the communication method is multicast in all the cases. So let's go back to our 6300 switch. Notice that we have, this is the uplink to the 8360. It is a lag and it is in layer 2 mode. However, there is no need to add the VLAN, the transport VLAN for PTP, because there's that is already happening without the need for clarification here. So because this is not originating nor receiving those packets, it is only forwarding those packets across its own ports. It does not need to show what the VLAN is, because that's already happening over VLAN 240 in this case. You have to make sure that VLAN 240 exists, etc., but that is not necessarily a PTP issue. The other thing that you see is that the member ports, ports 24, 224, and 124 are part of that lag. And the member ports do not need to, you do not need to set up a PTP role. Again, packets are coming and going through the right ports without having to add that here. The downlinks, or the ports that we're using to connect to our ordinary clocks, this is what we have there. And now we can take a look. So if we want to know what is going on from the point of view of the sources here, what we can do is show PTP, and you can take a look at the clock. And notice that most of the information is not available because, again, this is in transparent mode, so it does not see priorities, clock quality, etc., or the offset, because it's not synchronizing its own clock. So transparent mode is a lot simpler. Let's take a look at the statistics. And again, there are no statistics available for the transparent clock. So if we want to know the effect of the transparent clock for our ordinary clocks, we need to go back to those devices, in this case to our clients in the Ixia box. And we see here, we want to see the statistics for these. So we go to the PTP drill down parameters here. And what I will do is I will reset these statistics and see them from the start. So we see how they evolve, and I will say automatically refresh statistics. And you will see that the maximum offset will go eventually up to 70, 80 nanoseconds. And the path delay is a bit longer. And the path delay is longer because we have the 6300 between these clients and their source, which is the 8360. So the path delay here is longer than what we had seen on the boundary clock, because remember here we have 2 hops to get to the source, while before we had only 1. So with that, we have everything that we need to see in terms of the relationship between the boundary clock, the transport or the transparent clock in between, and the ordinary clocks at the end of the chain. So again, we have allowed for some time to pass, and we see the offsets in nanoseconds are within the 100 nanosecond range that we expect. So even the transparent clocks are very efficient in terms of PTP
synchronization. Let's take a look at some troubleshooting tips. First of all, if you are having problems with Ptp, as with anything in the network, start by checking connectivity by using pings and trace routes, in this case between sinks and sources. But you also, if you have transparent clocks in between, check that you have full IP connectivity or Ethernet connectivity if that's what you're using as your transport mode. If you need multicast routing, check the M routes in the IGMP groups. Make sure that sources and sinks can communicate with each other by using multicasts. Verify the source clock. Check the Ptp parents and see that it is connected so that this device in particular is connected to the right parent. Check all the boundary clocks interfaces in the case of a boundary clock, and the same would apply to a transparent clock by using the show Ptp interfaces command, and then check the boundary clock's offset and repeat that several times. Use the show Ptp clock for that. That will give you an idea of the how well your boundary clock is synchronizing to its own source or its own reference clock. Take the COPP statistics for package drop, and finally check if the boundary clock's state is phase aligned. We'll get to that in a second, and I'll tell you what that means now. So let's take a look at the different commands that we mentioned before. So the show Ptp interface brief will tell you the role that each port is having, and this display here is from a boundary clock. It's showing you that port 1 is a sink, so that is my connection to the parent, and then the lag 240 is a source to for some sinks. Port 2 here is showing as a source, but we know that this is a another link to a second ground source in this case, and the default state is source. So it will be in source mode, but it's actually idle. It's not acting as a source of any clients. There's no client connected to that device or to that port. So the Ptp parent, you can check the parent clock ID. And in this case, the parent clock, as you can see, is the same as the ground source clock. And the other thing that you can see is that based on the class, etc., in the priorities, the MAC address was used to select the ground source clock. And here's the initialization process and what we said about the Ptp clock being in phase aligned state. Again, this applies to a boundary clock, and this is probably one of those things that you have to verify once the clock has started. Let's say after 10-20 minutes of the clock running, make sure that it's reached the phase aligned state. What does that mean? So the initialization process of a boundary clock has two big steps. The first one is the selection of the parent. And that's what we mentioned earlier about using all those parameters to select the parent. In this case, you can see here that once the parent has been selected, the interface that connects to that parent goes into clock sync state, and the other port that goes to a different parent candidate goes back into source state. So it went through passive state and now it's in clock source state. Once that is done, the boundary clock continues its initialization process by starting a stage called calibration. I will not go into the details here, but the three calibration steps are acquiring, frequency lock, and phase align. So once a clock has locked its frequency and aligned its phase to its parent, then the clock is ready to provide good quality time sourcing for clients. So until the clock is fully calibrated, the quality of your synchronization process might not be the best. And this is key. So whenever you have a bounded clock that just started and connected to a ground source or to a parent, or whenever there was a failover, check this the event log for the state of the Ptp clock. So troubleshooting and final details you have here with the show Ptp clock. You see the configuration that you're having, but again, the most important part is to take a look at how well you're synchronizing and look at the offset from the source clock. And notice that in this case, it's showing 10 nanoseconds, but it will vary, and it will vary with each synchronization cycle. And remember, the offset is the deviation from the source. If you see this number growing beyond 100, then you have to start looking at what is going on in the network, and also check if your system, the system that you're providing synchronization for, will support what is the maximum offset that it can support. Ptp interfaces, show Ptp interfaces here. You can look at the port state, and also in this case, because it's a link aggregation group, it shows you which one is the primary and the secondary interface. And again, Ptp, just check the package drop with in the COPP. Again, just in case, remember, packets arrive at the ASIC, and from the ASIC will go to the CPU for processing. And that path is the one controlled by the control plane policy that is applied. So COPP controls the traffic between the ASIC and the CPU. And that's where you cannot allow Ptp packets to be dropped. So monitor this from time to time, especially if you're adding more clients. With that, thank you.